Hello everyone, hope you're all doing fine. Welcome to the second lecture on electrostatics. In this video, we're going to learn about most fundamental law of electromagnetism, that is Coulomb's law. Coulomb's law, which tells us about how the charges interact with each other, how strong the force between them is. We'll also learn some important properties of electric force, followed by the limitations of Coulomb's law. We'll wrap up this video by solving some example problems on Coulomb's law. By the end of this video, you'll be able to understand the entire concept of Coulomb's law, and you'll also be able to solve some numerical problems, some numericals by using Coulomb's law. So yes, my name is Vijay Krishna and you're watching up this channel. Let's get started. Coulomb's law. Coulomb is a scientist name whose full name is Charles Augustin de Coulomb. So he has proposed the Coulomb's law, who has studied the electric force between the charges both qualitatively and quantitatively. According to Coulomb, the electric force between the charges, which are obviously stationary, electric force between the charges is directly proportional to the product of their magnitudes. Product of their magnitudes. The product of the magnitudes of the charges, and it is inversely proportional to square of the separation between the two charges. I'm drawing the diagram here by representing the two charges and showing the separation between them. So I'm taking charge Q1 here, and at certain separation charge Q2 I have placed. Separation between the two charges is R, which is center to center distance. If Q1 and Q2 are the two charges which are obviously at rest, which are separated by distance R, then the force between the two charges F is directly proportional to Q1, Q2, product of the magnitudes of the two charges, and it is again inversely proportional to square of the separation between the two charges, which is R square. Now if I want to combine these two relations, I will be getting F is proportional to Q1, Q2 upon R square. So in order to remove this proportionality here, I have to introduce a constant which has been already introduced by Mr. Coulomb. So F, electric force between the two charges, is equal to some constant into Q1 Q2 by R square. Here K is the proportionality constant which is introduced by Mr. Coulomb. So this constant is further named as Coulomb's constant. Coulomb's constant. When this entire analysis is performed in free space, air medium or vacuum medium, then this K value comes out to be 1 by 4 pi epsilon naught for free space. So this K is equal to 1 by 4 pi epsilon naught. What is, we know the pi value, which is 3.14 or 22 upon K, 22 by 7. Then we don't have the idea on this epsilon naught. Epsilon naught is the permittivity of free space, in our case. Permittivity of free space, and its value is 8.85 times 10 to the minus 12 Coulomb square per Newton meter square. So this is a constant which has some units, Coulomb square per Newton meter square, epsilon naught. If I substitute this epsilon naught value, which is 8.85 into 10 to the power minus 12 in here, what am I getting for the K value? K value comes out to be 1 by 4 pi times 8.85 into 10 to the minus 12, which gives a result of approximately 8.99. I'm rounding the value to 9 into 10 to the power 9. I can write the units over here, which is Newton meter square per Coulomb square. So we have discussed about two constants. One is Coulomb's constant which comes out to be 9 times 10 to the 9 Newton meter square per Coulomb square, and the other constant is permittivity of free space, which is 8.85 times 10 to the minus 2 Coulomb square per Newton meter square. So you may be wondering how these units have came. Okay, so let's understand how these units have been defined. Okay, so first K. So we have this F is equal to K times Q1 Q2 by R square. I am rewriting the equation for K. So this K is equal to F times R square cross multiplication and divided by Q1 times Q2. So force unit is Newton and the separation unit is meter, which has the square, so I am putting square for the unit as well, divided by Q1 is the charge of one particle, which is Coulomb, whose unit is Coulomb. Again, charge of the other particle is also Coulomb, I am putting square. So I am getting the unit of K as Newton meter square per Coulomb square. Newton meter square per Coulomb square. Unit of Coulomb's constant. If I want to define the dimensional formula for this Coulomb's constant, I am writing here dimensional formula of Coulomb's constant K. I can derive this dimensional formula simply by using the unit as well. So this K unit is Newton meter square upon Coulomb square, right? So Newton, dimensional formula of Newton is mLT minus 2. Newton is the unit of force, so F is equal to ma. A is nothing but LT minus 2, and meter square. Meter is the unit of length or separation or distance, so I am writing L square here. Now see, Coulomb is not a fundamental quantity, rather it can be derived, the dimensional formula of Coulomb, the charge can be derived from ampere and time. So the dimensional formula of Coulomb is ampere time. As it has square, I am placing squares for both of them. So if I rewrite this dimensional formula, rearrange this dimensional formula, what am I getting? M is there, L, L2, L3 is there, and in the denominator we have t square and we have t to the minus 2. If I correctly write this one, t to the minus 4, and finally we have a2 in the denominator. If I take this to the numerator, a minus 2. This will be our dimensional formula of Coulomb's constant. Now coming to the second constant, which is permittivity of free space. Now permittivity of free space unit is we can derive this unit by using the same equation itself. So I have the force is equal to 1 by 4 pi epsilon naught times q1 q2 upon r square, right? Now if I want to write the units of epsilon naught, I am rearranging the equation for epsilon naught, which is 1 by 4 pi, which is obviously constant, we don't have to worry about it. So q1 q2 by fr square, now I want to define the units for this quantity epsilon naught. So q1, unit of q1 is Coulomb, unit of q2 is also Coulomb, so I am squaring it up. Now force unit is newtons, and then r is the separation between the two charges, which is distance, so the unit of distance is obviously meter square. I am representing all the units in SI system. Okay, now if I want to define the dimensional form, this is the unit of epsilon naught, unit of epsilon naught. Okay, now if I want to define the dimensional formula of the same quantity, which is epsilon naught, permittivity of free space. Now as I know, Coulomb is not a fundamental quantity, rather it can be derived from the fundamental quantities, which are ampere and time. As it has square on it, so I am squaring these two things. Now Newton is mLT minus 2. Now we left with meter square, which is L2. We can simply reciprocate to get the dimensional formula. What are we getting? What are we getting? M minus 1. This m can be taken to the numerator, and we have L3 here. So L minus 3, and we have T minus 2. If I take it to the numerator, T to the 4, and what am I left with? I left with A2. So this is the dimensional formula of epsilon naught. Dimensional formula of epsilon naught. Though these two quantities are constants, these two will have the units as well as the dimensions. I've defined both the units and dimensions of these two quantities. So let's come back to the actual discussion, which is force between the two charges. I have given all the details because I don't want to miss anything. So coming back to the actual point, which is force between the two charges, which is given by F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square, where 1 by 4 pi epsilon naught is the permittivity of free space, and this equation is meant only for free space when the two charges placed in the free space. Now what if I want to place these two charges in some other medium, let's say water or some other medium, any other medium. Let's say I have placed these two charges in some other medium. Now if I have placed these two charges in any other medium, now the force would become, so here I have placed Q1 and Q2. As I have already told you, the charges will not change with the medium, rather the force between them changes. So that we can evident from here. So Q1 and Q2 I have placed in some other medium of permittivity, epsilon. Okay, right. Let's say these two charges placed in the medium of permittivity epsilon with separation R again. Okay, now the force between the two would become 1 by 4 pi epsilon. In the earlier case it was epsilon naught because it was representing the free space or air medium or vacuum, as you can say, but in this case this epsilon is the permittivity of the medium in which the two charges are being placed. Now Q1 Q2 upon R square. But we don't know the value of epsilon, right? We know the value of epsilon naught, but we can calculate the value of epsilon. But anyhow, I'm going to define a new quantity here so that we need to remember, which is relative permittivity. Relative permittivity, which we also call it as dielectric constant. Dielectric constant. We usually represent relative permittivity with epsilon R, and this dielectric constant is often represented with K. Both of them are same, even if you represent it with epsilon R or you can represent it with capital K. Both of them are same. So both of them are representing the same quantity. So epsilon R or dielectric constant K. Okay. So yes, relative permittivity, dielectric constant, epsilon R or K. Okay. Now this epsilon R can be defined as the ratio of permittivity of medium to the permittivity of free space. It is actually a ratio. So it can be defined as the ratio of permittivity of medium to the permittivity of free space. Epsilon is the permittivity of medium and epsilon naught is the permittivity of free space. The ratio of these two will give the value of relative permittivity. If I rearrange this equation for epsilon R, epsilon naught. Now I can replace this epsilon with epsilon R, epsilon naught, or I can write capital K times epsilon naught. Capital K times epsilon naught. If I replace epsilon with K epsilon naught in here, the earlier K was Coulomb's constant, which was represented with small k. But here in this case, capital K is the dielectric constant or relative permittivity. Okay, so capital K is different from small k, that we need to remember. We don't want to confuse. Okay, so capital K. So if I replace this one over here, Now force would become 1 by 4 pi epsilon naught times epsilon r. So I am writing epsilon naught here and I am writing epsilon r 1 by. Okay, it makes no difference, we'll be getting the same result. So, and we left with multiplication of charges q1 and q2 upon r square again. Now I know the whole thing here to here, 1 by 4 pi epsilon naught q1 q2 by r square. What is this quantity? 1 by 4 pi epsilon naught q1 q2 by r square. This f, this k can be replaced with 1 by 4 pi epsilon naught. I am writing here 1 by 4 pi epsilon naught q1 q2 upon r square. So 1 by 4 pi epsilon naught q1 q2 by r square, here f. So this f is the permittivity of free space. To differentiate, to distinguish the two forces, I am representing the force between these two charges when they are placed in some other medium of permittivity epsilon. So this is f dash and here it is f dash. So this f dash can be further written as 1 by epsilon r. This whole thing is nothing but f. Whole thing is nothing but f. I can also write 1 by epsilon r can be written as k itself and force. So what I have noticed here is when we take the charges to some other medium of dielectric constant k or epsilon r, then the electric force between the charges decreases by 1 by k times. I am repeating the statement again. If I have taken the charges, I am measuring the force between the charges and I have taken the charges, I have put the charges in a medium of dielectric constant k, in such case the electric force between the two charges would reduce by 1 by k times than the force when two charges placed in the free space or air medium. Okay, so it is completely evident that the electric force between the charges depends on the medium itself. Okay, I hope I made the point clear to you. I hope this entire thing is understandable. If you have any doubts regarding the explanation so far, you can comment below in the video. So let's go further. Okay, so these are the basic information about Coulomb's law. Now coming to the overall equation for the electric force between the two charges. This force F is equal to 1 by 4 pi epsilon naught times 1 by k. Here this is capital K again, I am repeating, q1 q2 upon r square. So this is the ultimate equation for the electric force between the two charges of q1 and q2 charge separated by distance r in the medium of dielectric constant k. Okay, in this equation each of the quantity is representing something, which is F representing force between the charges, K representing dielectric constant, and epsilon naught is the permittivity, which is again constant. Q1 and Q2 are the charges, R is the distance between the charges. Okay, now I have got 4 different quantities involved in the equation, and we have also one more quantity, which is epsilon naught. Epsilon naught is a constant value. Even if you take it to some other medium or any other planet, epsilon naught is a constant value. Okay, so that's the reason I have considered it as this whole thing as a constant, and I have taken the rest of the quantities which can be varied. This can be varied with the medium. As medium changes, force also changes. This can be varied with charges, distance, medium. So everything can be varied according to the requirement, of course. So as I have 4 quantities here, if I want to define the relation among any two quantities, okay, between any two quantities, I have to keep the rest of the 2 quantities as constant. That's for sure, right? Hope I made the point clear here. If I want to define the relation between any 2 quantities among the 4, I have to consider the rest of the 2 quantities as constants, right? So I'm using the same key point here to define the relation among different physical quantities, which involves 4 physical quantities here, right? Okay, let's define. Okay, case 1. what I'm going to do is I'm considering f and q1 q2 are as variables, f and q1 q2. One moment. F1, Q1, Q2 as variables, rest of the quantities as constant. K and R are constants. I put these two quantities as constants. Same medium, same separation between the two charges. But in this case, I am varying the charges, accordingly the force also changing. So, K and R have been kept constant. Now, force between the, force is proportional to Q1 and Q2, which we already know from the equation and from the definition as well, from the statement as well, right? F is proportional to Q1 and Q2. So if I increase the charge, then the force also increases only if these two things are constant. These two quantities are constant, okay? So if charge is increased, any of the charge or both of the charges is increased, force also increases and vice versa. If charge decreases, force also decreases, okay? Right, now coming to the second case. In this case, I'm going to keep K and Q1, Q2 charges as constants. In this case, I can define the relation between F and R, which we have already defined. F is proportional to 1 by R square, or we can simply say F is inversely proportional to R square. F is inversely proportional to R square. As the separation between the two charges increases, obviously the force between the two charges decreases. So I'm rewriting F1 R1 square is equal to, I can rewrite this one. So F R square is equal to constant. F R square is equal to constant. So for that, F1 R1 square is equal to F2 R2 square. F1 R1 square is equal to, right, understood. F1 R1 square is equal to F2 R2 square. Here F, okay, understood. F1 R1 square, F2 R2 square. This is one result. We are just playing with the Coulomb's law equation. There is nothing much is happening. We are using the Coulomb's law and we are just playing with the Coulomb's law. We are getting the relation among different physical quantities which are involved in Coulomb's law equation, electric force equation. Okay, so these are the two results that we have got so far. Now let's move on to the next result. Let's take I want to keep the constant, K and F, Q and R as constants. Now if we talk about case 3, Q1 Q2 and K and Q1 Q2 and R as constant. Q1 Q2 and R as constant. Now if these two are constants, then Q1 Q2 and R as constant, Q1 Q2 and R are constants. If these two are constant, I can define the relation between force and dielectric constant. So from the equation, F is proportional to 1 by K, where K is dielectric constant, not the Coulomb's law, Coulomb's constant. So this Fk is equal to what? Constant. Now F1 K1 is equal to F2 K2. This is the other result. Okay, now if I go to the fourth case, let's just say to keep the force and Q1 Q2 as constants. Now I can define if Q1 Q2 and force as constant, I can define the relation between R and K. Now as we have the formula, F is equal to 1 by 4 pi epsilon naught 1 by K times Q1 Q2 by R square. As I've already told you, this force is constant, this entire thing is constant, force is defined as constant, Q1 Q2 is also constant. These three things are constants, right? If I rearrange this equation, K R square is equal to constant, right? In such a case, K1 dielectric constant of medium 1 R1 square is equal to dielectric constant of medium 2 R2 square. This is one such very good result where we can use it in the numericals, in which Coulomb's law can be used. Okay, so so these are the cases where we have related different quantities in the Coulomb's law equation, electric force equation, a relation between the two by keeping the rest of the two quantities as constants. So I hope these relations have been understandable, have been cleared out for you. Now let's move on to the next point of discussion, which is properties of electric force. So far we have been discussing the concept of electric force by using Coulomb's law, right? So let's understand some properties of electric force between the charges. First point is, it is analogous to gravitational force. Let's understand the term analogous, which is almost similar, not exactly similar, almost similar, analogous to gravitational force. So as we all know, the gravitational force between any two masses in the universe is given by G m1 m2 upon r square. If I write the equation for electric force between two charges is K q1 q2 by r square. If you look at the two equations, they are resembling the same terminology. If we focus on the first equation, gravitational force, G is universal gravitational constant, which is constant, and this K is Coulomb's constant, which is also constant, but the difference is a slight difference. G is independent of the medium, wherever the masses have been placed, it doesn't matter, the value of G will remain constant. But if you and masses m1 and m2, m1 masses are the fundamental property of the bodies, like charge. Charge is another fundamental property of the bodies. Okay, so as mass and charge are fundamental properties of the bodies, so these two are also resembling the same. Now r square, distances are obviously the same representation we have provided. So as these two are constant, these two are fundamental properties of bodies, and r square is again separation between the bodies. So we can say this gravitational force is analogous to electric force, electrostatic force. I hope I have cleared this first property of electric force, right? So now coming to, and the one more point I missed to explain, this K depends on the medium, as we have already discussed. Now it obeys inverse square law. First point which have been already discussed. Second point, it obeys inverse square law, which is evident here. This electric force is given by some constant, Coulomb's constant K, q1 q2 upon r square. This force F is proportional to 1 by r square, which is inverse square. Force is inversely proportional to r square. That means it obeys inverse square law like gravitational force. Gravitational force also obeys inverse square law. Now coming to the third point. This force depends on the medium. That is, we have already evidenced it, and we have already got the conclusion from the equational result. So this electric force depends on the medium, and we have derived the relation between the two. F is inversely proportional to the dielectric constant of the medium, where K is dielectric constant. Dielectric constant, right? So this force depends on the medium. That means the electric force between the charges changes with the medium, right? Now it is a central force. Very good property, right? It is a central force. What do you mean by this central force? Central force is something, the force acts along the line joining between the objects. Okay, when you look at the gravitational force, let's say I've taken two objects separated by center to center distance is r. If this is m1, this is m2, then this object will attract this object, and this m1 attract m2. Action reaction pair of forces. These two forces are acting in the same direction, right? Not in some other direction, this way or this way. So these are wrong. These are two opposite forces. They may be equal, but these two forces are not along the line joining the two objects. Okay, so for this force to be central force, the force between the two charges or the two objects must be acting along the line joining the two charges only, two objects only. As this force, electric force, is acting along the line joining the two charges, this force is to be treated as central force. Okay, let me explain it again. I've taken charge q1 and charge q2. Separation between them is r. Now this q1 and q2 are similar type of charges, similar nature of charges, both are positive, okay, like charges. That means there will be repulsion exist. This q1 must be pushing this q2 away, and this q2 is also pushing q1 away. Now q1 exerting a force on q2. Force on q2 due to 1 is to the right, and force on 1 due to 2 is to the left. But however, these two forces are acting along the line joining the two charges only. That's why we call this force as a we treat this force as a central force. Okay, right. Moving on to the next point, which is it is a conservative force, which is another most important key point or property of the electric force. What do you mean by conservative force? So whenever the conservation of energy concept is involved, we can use this force, work done by this force, right? So conservative force in the sense it is independent of the work done by this force is independent of the path followed. Okay, let me explain how this dependence or independence of path followed will work. Okay, let's take an object here. Okay, now weight is acting vertically downwards, obviously. Okay, now I've taken this object straight up to a height h. What is the work done? mgh. Okay, if I would have taken the same object in some other direction to the same point, to the same height, again the height would be h only. Now again, what is the work done? mgh. Work done by gravity is mgh in both the cases. Work done by gravity is mgh, work done by gravity is mgh, okay, in both the cases, minus, okay, because mg is acting downwards, which is displacement is upward, minus. In both the cases, work done by gravity is same. It is independent of the path forward. So we can say the gravitational force is a conservative force. Similarly, the electric force between the charges is also, work done by the electric force is also independent of the path followed by the particles or charges. Okay, let's just say for the electric force, I've taken one charge here and the other charge somewhere at infinity. I've taken this charge in some other path and I took this charge to somewhere here in the vicinity of the first charge. Now I took the same charge the other path and I took the same charge along the straight path. It doesn't matter what path we have taken the charge, okay, the charge has taken to reach this point. It doesn't matter. Whatever the work done by the electric force is independent of the path followed. That is why we call this work done, this force as a conservative force, right? So I'm writing the statements here. Electric force acts along the line joining between the two charges, okay, so it's a central force. Now work done by electric force is independent of path followed by charge. So we call this force as a conservative force. I hope the properties have been understandable. I have made every property of the electric force between the charges clear to you. If you still have any doubt, please comment below so that I can explain it further. Now let's move on to the next property, which is the force obeys Newton's third law. As I've already drawn in the next earlier slide, this Q2 is exerting force on Q1 in this direction, leftward direction, and Q1 is exerting force on Q2 in the rightward direction. However, these two forces are equal because the two charges involving the forces same, and the separation between the two charges in both the cases same. So constant is obviously both of them are placed in the same medium, so force between them would be same. Now how this Newton's third law of motion can be justified by using this electric force. Let's use the basic analysis to prove this one. Okay, now I have the force F is equal to I'm simply writing it as K, small k, Coulomb's constant, Q1 Q2 by R square. Okay, now I'm drawing the diagram here. Q1 and Q2, both of them are separated by distance R. Okay, now I'm representing the force on 2 due to 1. Force on 2 due to 1 is equal to K is a constant, Q1 Q2 by R21 square. R21 is the distance of 2 with respect to 1. Distance of 2 with respect to 1, or position of 2 with respect to 1. Okay, because we are defining the force on Q2 due to Q1. Now if I want to find the force on Q1 due to Q2 is equal to K Q1 Q2, I can write Q2 Q1, Q1 Q2 Q2 Q1 makes no difference here. So R12 square, R12 square, because I am defining the force on Q1 with respect to Q2 due to Q2, I am defining the distance of Q1 with respect to Q2, position of 1 due to 2. Okay, if I want to write these expressions in vector notation, I can simply multiply the entire equation with a unit vector. In which direction? In the force direction itself, right? So in the force direction means R21 unit vector, right? Now coming to this one, it should be R12 unit vector, R12 unit vector. Now from vectors representation, this R21 is towards the right and R12 is to the left, but however the separations are same. Okay, I'm rewriting R21 unit vector is equal to R12 unit vector. The magnitudes are same, but they act in opposite directions. So okay, R21 is equal to R12. Magnitudes are same, but they pointed in opposite directions. If I use these two relations, what am I getting? So use these two relations. F21 vector rotation is equal to K is again same, Q1 Q2 upon R21 can be written as R12, R12 square, and again R21 can be written as minus R12 because it is a vector and it is a scalar. So scalars I can replace directly without using negative sign, but here in this case vector notation minus R12 unit, right? So once I take this negative sign out, I am getting K Q1 Q2 upon R12 square R12 unit vector. I know this entire thing. What is it? F21 vector is equal to minus of, what is it? F12 vector? Yes. So F21 is equal to minus F12. That means if this is action, this could be reaction. If this is action, this is reaction. For every action there is an equal and opposite reaction. What is third law? Newton's third law says for every action there is an equal and opposite reaction. That means two equal forces acting in opposite directions on two different objects, right? Same point can also be applied here. Two different forces F21 and F12. I'm representing F21 force on 2 pushing away, force on 1. Both are acting in opposite directions and both the forces are acting on two different objects, right? And both the magnitudes, both the force magnitudes are same. That means this electric force obeys Newton's third law. Newton's third law. I hope I have explained it very clearly. If you still have any doubt, you can comment below. Right. Now, coming to the next one. Principle of superposition. Okay. As we all know, force is a vector quantity. Any force, even if it is centripetal force, centrifugal force, is also a vector quantity. So this electric force is also vector quantity. Force is a vector. So we cannot add the forces directly like we do for the masses. or for the times, because they are scalar quantity, they can be added directly. But when it comes to vector as a force, we cannot add them directly, rather we should add them vectorially. Okay, now let me draw the diagram. I have taken a point charge q and I have considered multiple charges somewhere around here and here. This is q1, q2, q3 and q4. Distance of q4 is r4, distance of q3 is r3, distance of q2 is r2, q1 is r1, let's say. Now every charge is, exerting some force on capital Q charge. Now I am writing every individual charge here. So this, okay, okay, so force F1 is equal to Q1Q upon R1 square. F2 is equal to K Q2Q upon R2 square. Similarly, F4 is equal to K Q4Q upon R4 square. And Q3 is also there, F3 is also there, but anyhow, there are multiple number of charges which are exerting a certain force on Q. So as you can see, all these forces, this Q1 is pushing this charge in this direction, and this Q2 is pushing this charge in this direction, Q3 is pushing this charge in this direction, and Q4 is pushing this charge in this direction. This is F4 and F1, what is it, F3, F2, F3 and F4. All these forces are acting in almost different directions, right? So we cannot add them directly. Okay, so we can rather add them vectorially. So F net on capital Q, F net on capital Q, okay, F net on capital Q is equal to F1 vector, so I am representing it as vectors, F2 vector plus F3 vector and so on, as many number of particles as you can place. So net force on any charge is the vector sum of all the individual charges. I want to repeat the statement again. The net force on any one charge is the vector sum of individual forces on the same charge due to all other charges. So this is what we call it as principle of superposition. Now we are left with one more property, which is electric force between two charges does not changes with the presence of any other charges. Let's say I have taken two charges. Okay, I am drawing the diagram here. So I have taken two charges Q1, Q2, okay, separated by a distance R. Now the force between them is F is equal to K Q1 Q2 by R square. Now let's assume I have taken a third particle. I have placed it somewhere here, Q3. So we may think that we may use the misconception like if I place Q3, the force between these two charges may get affected, but it will not actually get affected. It will not change. But the net force on every individual charge changes. Let's just say this charge is not there. Okay, the force on Q1 is this one. This one, right? Force on this Q1 is this one. But when I place this Q3 is also exerting some amount of force, right? So directions are getting affected. Okay, sorry. So this force, I'm writing it right here. So F is equal to K Q1 Q2 by R square. Q1 Q2 by R square. I am naming this force as F1. Okay. Now this Q3 is also exerting some force on Q1. In this direction, because it is also pushing this charge. F is equal to K Q1 Q3 by R square. Okay, again this is also R. Let's assume. See, the net force get affected, net force on every individual charge get affected, but it will not affect, presence of any other charge will not affect the force between any two charges. There is a difference. Okay, so if any third charge is placed near the two charges, it will not affect the force between other two charges, rather it affects the net force on any individual charge. I hope the last point is clear to you, is very well understandable to you, right? Okay, I have explained all the properties of electric force. Now let's move on to the next step, which is limitations of Coulomb's law. Now coming to limitations of Coulomb's law, like every law does, Coulomb's law also has some limitations. The first limitation is it is applicable only to the point charges. Okay, or even if you take a larger objects, the separation between them should be greater enough to consider the two bodies as point objects. Okay, so the Coulomb's law is applicable to point charges. Okay, first one. Second one is stationary charges. For the Coulomb's law to use, the charges should be at rest. Charges are to be assumed at rest. Otherwise, Coulomb's law will not be applicable. Okay. Now, the third one is distance rays. Actually, as we are dealing with electric forces in Coulomb's law, so the size of nucleus is approximately 10 to the power minus 14 to 10 to the power minus 15 meters, which is approximately 1 femtometer. So this force will not work below this value. Okay, below this value, because size of nucleus is very small. We cannot keep the objects below this value. I mean 10 to the power minus 16, 10 to the power minus 17, 10 to the power minus 30, which is even complicated. So it will not work the distances below 10 to the power minus 15 meters, 1 femtometer. Okay, so distance range is above 10 to the power minus 15 meters only. We can even place 10 to the power minus 15 or 10 to the power minus 14, minus 13, minus, we can increase the value, but we can increase the distance, but we cannot decrease below this value. Okay, so R should be greater than 10 to the power minus 15 meters. Should be greater than 10 to the power minus 15 meters. And so charges must be at rest. Stationary charges only it is applicable for stationary, and it is applicable to point charges. These are the three limitations or drawbacks that the Coulomb's law has. Okay, right? So let's move on to, let's discuss some, let's solve some numerical problems. Okay, now let's look at the first problem on Coulomb's law. Read out the question first. Let's understand the question. How, 2 point charges, 4 microcoulombs, 8 micro. As I've already told you, 1 coulomb is a very large value. So we represent the charges in terms of, unit of charges in terms of micro, milli, nano, pico, femto. These notations we use. Okay. 2 point charges, 1 microcoulomb, 8 microcoulomb, 4 microcoulomb and 8 microcoulomb are placed 0.5 meters apart in free space. Okay. Free space. Find the electric force between them. It is a basic formula. Basic question. We use the Coulomb's law equation to find the force between them. F is equal to constant K Q1 Q2 upon R square, and we know the value of K when the two charges placed in free space. This K value is 9 times 10 to the 9 for free space, and Q1 is, I am writing the given quantities, known quantities obviously, Newton meter square per Coulomb square, which we have already discussed. It's not K1, it's K. Okay, now Q1 is equal to 4 microcoulombs, which is 4 times 10 to the minus 6 coulombs. Q2 is equal to 8 microcoulombs, again 8 times 10 to the minus 6 coulombs, and the separation between them is 1.5 meters, which is half a meter. Okay, if I substitute all these values into this equation, what am I getting? 4 times 10 to the 6, 8 times 10 to the 6 upon 1 by 2 whole square. So, okay, so 4 8s are 32, 4 8 the 32, 32 nines. Okay, I'm rewriting this. 1 by 2 whole square, 1 by 4, 1 by 4 can be taken to the numerator, into 9, into 4, into 8, into 10 to the minus 3. 10 to the minus 3. Okay, now what am I going to do? Okay, 8 4 the 32, 32 fours. 34s are 120, 128 into 9 into 10 to the minus 3. So 9 8s are 72, 7, 9 2s are 18, 7, 5, 9 2s are 18, 7, 25, 9 1s are 9 plus 2, 11. 11 times 10 to the minus 3. If this minus 3, the point can be taken to this side. Okay, now what am I getting? 1.152 newtons is the force between the two charges. So where we can find this value? 1.28, 1.15, okay, 1.15. 1.15 is approximate value because no other value is matching. Okay, right? Hope this solution is clear to you. Let's move on to the next one. Okay, let's understand the question here. Two identical metal spheres possesses 60 coulombs and minus 20 coulombs of charges. Yes, very good question. So 60 coulombs minus 20 coulombs of charges. They are brought in contact and then separated by 10 centimeters. Okay. Now we are going to use the conservation of charge, which we have already learned in the first video. Okay, right. So let's use the conservation of charge. What is the charge which is initially given to you? Okay, that is 60 coulombs minus 20 coulombs. It is the algebraic sum of charges because charge is not a vector quantity, it is a scalar quantity. We can add them algebraically. So 60 minus 20 is 40 coulombs charge. As we all know, when the conductors, metals are conductors, right? When two metals put in contact with each other, charge flows from higher potential to lower potential until the equilibrium is applied. The equilibrium means potential same. As these two are identical metal spheres, the charge will also be same. Okay, at the end of charge transfer, the charges on both the spheres would be same. So Q final must be 2 times charge on each sphere, which is same. Now if I equate these two from conservation of charge initial is equal to charge final. Charge initial is equal to charge final. Charge initial is 40 coulomb, charge final is 2Q. That means charge on each sphere after the charge transfer, after they put in contact and separated, is 20 coulombs. Now the charge on each sphere is obtained. We can use the formula of electric force from Coulomb's law, 1 by 4 pi epsilon naught. We can use this quantity as constant K, Q1 Q2 by R square. Q1 Q2 by R square. As I am given with Q1 and Q2, which we already know, 20 and 20. R is nothing but 10 centimeters and 1 by 4 pi epsilon naught value is 9 into 10 to the 9. I am writing the values here. 1 by 4 pi epsilon, or you can simply write it as small k, is equal to 9 times 10 to the 9 Newton meter square per Coulomb square. I am writing the units every time because you will be able to remember it if you look at the units for multiple times. Right, Q1 is equal to Q2, which we have got 20 coulombs, and R is given as 10 centimeters, which if we convert it into SI system of unit meters, then 10 times 10 to the minus 2 meters. Okay, if I substitute all these values, what am I getting? F is equal to 9 into 10 to the 9, Q1 and Q2, which are 20 and 20, upon 10 into 10 to the minus 2 whole square. Let's solve this one. Okay, 9 4 the 36, 10 to the 9, 0 0, 10 to the 11, 10 to the 11 by 10 square is nothing but 100, 10 to the minus 2 whole square nothing but 10 to the minus 4. Okay, let's cancel these two things out. Minus 2 remains, and this, if I take this minus 2 to the numerator, what am I getting? 36 times 10 to the 11 plus 2, which is 13 newtons. 36 into 10 to the 13 newtons. I have already told you 1 coulomb is a very large value, so we are getting this amount of force by using just 30 or 20 coulombs of charge. Okay, right? Sorry, 20 coulombs of charge. So this is the answer. Now let's find where, in which option this value is provided. 36 times 10 to the 13. Option A. Sorry, option A is the answer. I hope the solution is clear to you, right? Let's move on to the next problem. Okay, now let's understand the problem here. Okay, n fundamental charges. How many charges are there? N fundamental charges of charge q. All of them are having charge q. That means total charge is equal to n times q. It is something like 1 pen cost is 10 rupees, 100 pens cost is 100 times 10. Similarly, if one particle charge is q, then n number of particles are there. That means total charge is n. Okay, are to be distributed as 2-point charges. Now I have to distribute this nq, this entire charge, into 2 charges, q1 and q2. Let's decide how. 2-point charges separated by a fixed distance. Of course, the distance remains same in the entire analysis. Okay, that we have understood. Then find the ratio of maximum to minimum force between them. Okay, so I'm writing the force equation here from Coulomb's law. K q1 q2 by r square, and in the question it is mentioned this r square is constant, it's same in all the cases, and k is again constant. So I have to make this product maximum for force to be maximum. For force to be maximum, the product of q1 and q2 should be maximum. For force to be minimum, the product of q1 and q2 should be minimum. Right? Is the point clear? Right. Let's move. Okay. Now, to make this q1 and q2 maximum, to understand this, okay, let me take a number. Okay. In place of n, let's consider let 100 charges are there. 100 charges are there. Each of charge q. Okay. Now total charges q total is 100q. Now I have to divide this charge into 2 parts. One to acquire maximum charge, one other to acquire minimum charge. Let's say first division I have made is q 99q. Q19. Total charge is 100q only. First charge, one particle q1 I have taken it as q, q2 I have taken it as 99q. However, I am getting the total charge as 100q only, right? Okay. So if I multiply these two, q1 and q2 is equal to 99q square, right? Okay. Let's say I've taken 2q and 98q. These are q1, q2 quantities. Okay. 2q, 98q. Now q1 and q2 would become how much? 98 2s. 196. 196q square. Right. Now instead, what I'm going to do is I'm writing 50 50. 50 50. That means this could be the least combination, right? Least combination. Now if I write this if I write this q1 as 50q and q2 also 50q, then what happens? Q1 and q2 would become q1 q2 is equal to 50 times 50, 2500 q square. If you look at any combination, you will get less than this value. So it is evident that I'm writing q1 and q2. It is evident that if I divide the entire charge into 2 halves, I will get q1 and q2 as maximum. And if I divide the entire charge as one charge and the rest of the charges aside, then I am getting q1 q2 as minimum. Okay. So for minimum q1 q2 to be minimum, the best combination would be q n minus 1 q and n minus 1 q, right? And to get F minimum, I'm using the same combination K. Q1 is Q, Q2 is N minus 1 Q by R square, which is same in both the cases. So, and F maximum for Q1, Q2 to be maximum, Q1, Q2 to be maximum, the combination would be, the best combination would be, best combination would be NQ by 2 half the total charge and NQ by 2. Okay, now F max is equal to K Q1, what is, K NQ by 2, NQ by 2 divided by R square again, because the distance between them is unchanged. Okay, now the question is asked to find the ratio of maxima to minima. F max upon F minimum. F minimum. F minimum is equal to F max is how much? K NQ N square Q square upon 4. So K N square Q square by 4 R square by whole by whole by I'm writing the equation again, okay, is equal to K K N square Q square by 4 R square, N square Q square by 4 R square by F minimum K N minus 1 Q square by R square, N minus 1 Q square by Q into Q square and minus 1 R square. Okay, common terms can be cancelled, K cancelled, and Q square cancelled, R square cancelled. What are we remained with? F max by F minimum is equal to N square is left here by N square by 4. This N minus 1 can be 1 minus N minus 1, 1 by N minus 1. Okay, so this will be our answer. Let's find where this is given, N square by 4 N minus 1, N square by 4 N minus 1. This will be our answer. Right, hope you have understood the solution of this question. Right, it is a very good question. Okay, hope I have explained it very well. If you still find any difficulty in understanding this solution, please comment below. Now another question. Okay, let's understand the question. Two particles each of mass m carrying charge q are separated by some distance, any distance. If they are in equilibrium under mutual gravitational force and electrostatic force. So okay, q by m is of the order of, okay. Now the question is asked, in the question it is mentioned that the system is in equilibrium. That means there is gravitational force of attraction and there is electrostatic force of repulsion. Electrostatic force must be creating repulsive force, that the two charges must be pushing away, whereas the gravitational force is keeping them at the same place. Okay, now according to the question, system is in equilibrium means force due to gravity between the two masses, force between the two charges, electric force. Force by gravity is balanced by electric force, or electric force is being balanced by gravitational force. We know the formula for both of these forces. Gravitational force G m1 m2 by r square, K q1 q2 by r square. As these two have been mentioned as similar type, so m1 and m2 must be same, which is m. So I am rewriting the equation G m square by r square and K q square by r square again. R square will get cancelled. If I rearrange this equation, as we are asked to find q by m, charge by mass ratio, this q square upon mass square is equal to G upon Coulomb's constant K. Coulomb's constant K. Okay. Now if I want to remove the squares, square root is applied. Q upon m is equal to under root under root G by Coulomb's constant K. It's not the dielectric constant, it's the Coulomb's constant, and we know the values. And we know the values of G and K. We know the values of G and K. We know the value of G 6.67 times 10 to the minus 11. 10 to the minus 11. I'm not writing the units here. Anyways, you can write Newton meter square per kg square by K value is 9 into 10 to the 9 Newton meter square by Coulomb square under root. Okay, so I'm solving this equation 6.67 upon 9. If I take this 10 to the 9 in the denominator to the numerator, what am I getting? 10 to the minus 20 under root. And this is a quantity where we will get a 0 point or something. 6. I'm leaving it right here. 9 into this root is there. If I take this root of 10 to the power minus 10, 10 to the power minus 10, this could be 0 point something. So answer could be 10 to the power minus 10 or 10 to the power minus 11, depending on the answers given in the options. 10 to the power minus 2 is not the answer. 10 to the power minus 10 could be the answer. 10 to the power minus 11 is not there. So 10 to the power minus 10 will be the answer. Okay, right? Okay, so these are the problems we have solved just by using Coulomb's law, right? Yes, let's move on to the next example. Okay, yes, let's understand the question now. Two identical positive charges are fixed on the y-axis. Okay, let's draw the diagram of the given scenario. Okay, okay, right. So this is the origin, and I have considered two particles somewhere here which are at equidistance from the origin. This is Q and this is also Q, which are equal charges on the y-axis at equal distances from the origin O. Okay, that have been drawn. Now, a particle with a negative charge starts on the negative x-axis at a large distance from O, at a large distance, which is minus infinity, minus Q charge, which is started at a minus infinity, which is at large distance from O. Okay, okay, right. Moves along the x-axis, and passes through O and moves to the positive x-axis to very large distance infinity. Hope the given scenario is clear. I've drawn the diagram to understand it easily. Right. Its acceleration A is taken positive along its direction of motion. If there is acceleration along its direction of motion, then it has to be taken as positive. If the acceleration is opposite to the direction of motion, then it has to be taken as negative. Okay, that point is very clear to us. Okay, right. The particle's acceleration is plotted against its x coordinate. Okay, so graph has been plotted. Which of the following best represents the plot? That is quite a simple thing. Let's understand the equation. Okay, first, force acting between the charges K, Q, capital Q, or we can simply say force between the two, Q1 Q2 by R square. Q1 Q2 by R square. This force can be written as MA. If I take this mass out, I can write here, that means cross multiply. This A is equal to K Q1 Q2 by MR square. Now this K, M, Q1 Q2, none of these quantities are changing. Rather, the position is changing. R value, X value is changing. So I can write this equation as A is equal to constant by, in place of R, I can write X because I am dealing with the X axis. Okay, so A is equal to constant upon X square. So as you can see from this relation, as the separation is decreasing, the acceleration is increasing. Okay, X decreasing here as we go towards the origin. That means the acceleration is increasing. And tell me, acceleration is positive or negative according to given data. As it is mentioned that its acceleration is taken as positive along its direction of motion. As it is moving in this direction, acceleration is to be taken. If the acceleration is in the same direction, then acceleration is to be taken positive. Okay, let's see whether the acceleration is in the same direction or not. Okay, to understand that, as you can see, these two are positive charges, it is mentioned in the question, and this is negative charge. As it is moving towards the origin, these two charges are exerting more and more attractive force on this negative charge, right? As the force is increasing, as the separation is decreasing, force is increasing. As the force is increasing, the acceleration also increasing in the same direction. That means acceleration A in this portion is positive. That means y component must be positive. If we take the acceleration on the y axis and position on the x axis, y value must be positive. Okay, that we have understood. Now coming to the second portion. Okay, now as it passes through the origin, its distance increases. Here the distance is increasing. Acceleration must be decreasing. But in this case, still this negative charge might be somewhere here. Let's say minus q is here. In such a case, these two charges are attracting this negative charge towards the mean position, towards the origin. That means the acceleration is in this direction, whereas the motion of the particle is along the positive x. Acceleration is along the negative x, motion of the particle is along the positive x. So as the acceleration is opposite to the direction of motion, then acceleration is to be taken as negative. That means y component must be negative. Let's check. And it has to be satisfied. A is proportional to 1 by x square. That is the curved shape. Okay, right. When you look at the first graph, okay, at infinity, the acceleration is nearly 0, which these 2 points are right. Okay, as we are approaching the origin, the acceleration is increasing in the positive direction, which is also right. Okay, as we are moving away from the origin, the acceleration is decreasing, which is negative. Okay, this acceleration right here is maximum, right? And it is decreasing in the negative direction, right? This is also right. And as it moves to the origin, as it moves towards the origin, the acceleration, could be maximum, which may be, and then as it moves away, the acceleration could be 0 at some distance, at very large distance, it could be 0. So this could be the right answer for our given scenario. Let's check, and this is not possible, both of them are positive. Positive is, it can be correct, but this is wrong, and this is also wrong because it is decreasing and this is increasing. This is also wrong, and this is obviously wrong. Okay, right? So our correct answer is this one. Is the correct answer. I hope this logical explanation using our Coulomb's law equation is clear to you. I hope the entire explanation, entire solution, entire steps are understandable. So yes, let's move on to the next example. Okay, now nothing is mentioned here. Okay, let's define a question. Now I'm applying this Coulomb's law to basic mathematics. Okay, right. Let's take a charge. Here I have 1 Coulomb of charge. I placed 1 Coulomb of charge, and I have taken another charge of 1 Coulomb at a distance 1 meter. Another charge of 8 coulombs at a distance 2 meters. Another charge of 27 coulombs at distance 3 meters. Similarly, at distance 10 meters, I have placed 1000 coulombs of charge. Now, I have asked to find the force on 1 Coulomb charge. It is not as complicated as it seems. Okay, let's understand this one. Okay, now this 1 Coulomb force, 1 Coulomb charge is exerting repulsive force. Okay, this one, and this 8 coulombs charge is also repelling this, and this 27 repelling, 10 coulombs also repelling. All the forces are trying to push, all the charges are trying to push this 1 Coulomb away. That means all the forces are in the same direction. We can add them directly. Even if we take vector notation also, we can add them directly as all the forces are acting. Let's say I am applying 10 Newton of force with one hand and 10 Newton of force with the other hand, what is the net force on the object if I am applying the two forces in the same direction? 20 Newtons. Let's say I am applying force 10 Newtons, I am applying force 10 Newtons in opposite direction. It is 0. The object will be in equilibrium, right? So as all the charges are applying force in the same direction, so I can add them directly. So net force, F net, as we know, F is equal to K Q1 Q2 by R square. I am directly writing the numbers here. First this force, K Q1 Q2 by R square plus K Q1 Q2 by R square. Can I write this 8 as 2 cube? Sorry. Can I write this 8 as 2 cube? Okay. 2 cube, right? Now, K Q1 27 can be written as 3 cube by 3 square and so on. This 1000 K plus K Q1 10 cube by R square 10 square. Okay. Now I can take some of the terms common. K I am taking common. Here I am 2 square 2 cube cancel, 1 2 remains. 3 square 3 cube cancels, 1 3 remains. 10 square 10 cube cancels, 1 10 remains. Okay. So K I have taken common 1 plus 2 plus 3 plus so on plus 10. It is simply the sum of natural numbers. Sum of natural numbers. Sum of natural numbers. And sum of natural numbers formula I know, n into n plus 1 by 2. N into n plus 1 by 2. If I apply the same equation, this 10 is nothing but n. 10 is nothing but n. If I use this relation, k times n means 10 and n plus 1. 10 plus 1 by 2. By 2. What am I getting? So k 2 5s and 10 plus 1 is 11. 11 5 is a 55. 55 k. This will be our answer. So that is the net force acting on 1 Coulomb charge, which is exactly placed at this point, which is origin, I can say. Okay. So that is how we solve the given question by using, it is simply mathematical question because sum of natural numbers, just a little bit of involvement of Coulomb's law. Okay, right. Let's move on to the next example. Yes, okay, right. This would be our last example on Coulomb's law, and we'll move on to some other concept like equilibrium. Again, in that also we use Coulomb's law again, but with different strategies. Okay. Now I'm defining the charges here. Again, charge Q1. Sorry, charge 1 Coulomb, and here I have 1 Coulomb. Here I have minus 2 coulombs, 3 coulombs, minus 4 coulombs, so on. Okay, it is at 1 meter, 2 meter, 3 meter, 4 meter, and so on. Again, same thing, the force between the charges K, Q1, Q2 by R square. I am directly using the values here. Again, this charge is pushing this charge away, this charge is pulling it. So, towards left, toward right, right? All the leftward forces I am taking it as positive, all the rightward forces are taking as negative. So, negatives I am using. So, F net, force on 1 Coulomb charge, K Q1 Q2 by R square plus K, sorry, not plus, minus it should be, K Q1 Q2, so I can write directly as plus. I am directly using this minus 2 here, minus 2 by 2 square, okay, plus K Q1 Q2 by R square plus K Q1 Q2 by R square plus so on. Okay, now I am taking the common terms as common, similar terms common. So K I am taking out 1 minus 1 by 2 plus 1 by 3 minus 1 by 4, so on. No need to get confused. This is a familiar, expansion. We have an expansion like log 1 plus x. Log 1 plus x. It is expanded like x minus x square by 2 plus x cube by 3 minus x to the power 4 by 4 plus so on. This is the expansion for this log 1 plus x. Let's say x is equal to 1. Let x is equal to 1. If I place x is equal to 1, then ln 1 plus 1 in place of x, I am using 1. So this x is nothing but 1, x square is 1 again, 1 by 2 plus x cube is 1 again 3 minus 1 by 4. I am getting the similar expression right here, okay, for this log 1 plus 1. So I can simply write this result as k times this entire thing is log 1 plus 1, which is log 2. Log 2. So this will be our answer. This will be our answer. You may not be familiar with this expansion, but anyhow, trust me, this is one very good expansion in mathematics, and it is also helpful in our, So yes, that's it in this video. I hope the video is helpful. If you find any difficulty in understanding the video or any errors in the video, please don't forget to comment below. And if you find the video is really helpful, please like, share, subscribe, and don't forget to hit the bell icon in order to get the notifications as soon as I upload the videos. Thank you for watching. See you in the next video.